Okay, guys. So today we will be starting with a new unit called the gravitation. It's a very interesting topic, and we will be covering it in various videos. But for today, we will be mainly focusing on introduction of the gravitation and then the Kepler laws. Today in this video, we will study about the Kepler laws, all three of them, and we will practice some numericals on that basis. And then for the third law, I believe we will do a proof as well. Okay, and some questions based on that. So before we do that, let's understand what is gravitation, and what's the history of gravitation, and how does it relate to the motion of planets. So apparently, uh, from the ancient times, humanity was aware about our the existence of planets and their revolution. So during the ancient times, the sky for them appeared to be fixed, and it was known that there was at least 7 planets that move among the stars. So they were called planets at that time, or the wanderers in Greek. So first of all, like a theory given by a Greek astronomer, uh, Ptolemy, in 200 AD. In 200 AD, Ptolemy gave an idea of the geocentric theory. Remember, whenever the word comes geo, it means the earth, and centric means earth at the center. The theory was based on the fact or the observation that earth was stationary and all the sun and other planets were revolving around it. Obviously, we know now that earth is not the center, okay, but sun is center. But to begin with, this was the uh, theory that was given by the astronomers in the ancient times. So this was the geocentric theory, where earth was supposed to be the center. Yeah, but after that, uh, even at that time, around 200 AD, and after that, there were some physicists and I would say astronomers, mathematicians like Aryabhatta from the Indian subcontinent. He was the first to write down about another theory where the sun was supposed to be at the center and all the other planets were supposed to be revolving around that. So Aryabhatta was the first to give the actual theory. 746 AD, he was born at that time, and but in the West world, uh, the one who was able to this theory, the one who was able to change this theory of Ptolemy was Copernicus. So in very late, after around 1,000 years, Copernicus was able to convince others that sun was indeed at the center of the solar system, or whatever the planets we could see at that time. Only we didn't have the Hubble Space Telescope or strong telescopes like that. We simply had our simple telescope like shown here. So the Aryabhatta already given, and then Copernicus in 1473 they gave the theory called the heliocentric model. See, whenever you hear the word helio, it means the sun. Helio, and heliocentric model means, yes, where the sun is supposed to be the center, and the star, that is sun is a star, so it was the center and all planets are revolving around it, just like the earth here. Let's say it was a sun, it's a sun. So uh, as we can see here, the gravity is working like this. It's like a net, and the heavier the body, the other bodies will then revolve around it. If it is lighter, other bodies won't revolve around it, it will be the other way around. So this was the heliocentric theory. This was the history of what we can say, the our understanding of the planets and the and celestial objects. So sun-centered theory, And helio, you remember that helio means sun. Now, this is also called as Copernicus theory. Nevertheless, I'll tell you one more interesting thing about this, that uh, even this heliocentric theory was incomplete. I will tell you one thing, that uh, Copernicus gave the idea that all the planets revolve around the sun in circular orbit. The orbit is circular. However, in reality, this is not the case. In reality, that is not the case. The thing, the observation done by a Danish astronomer, he was from Denmark, so I think his name was Tycho. Tycho was the astronomer. He made a accurate measurement of the position of stars and planets. He did some measurements. So that data was analyzed by our uh, scientist Kepler. Kepler astronomer was the one who analyzed the data of the Danish astronomer. He observed that the planets were not revolving around the sun in circular orbit, but according to the calculations, the revolution was elliptical in motion rather than circular. See, elliptical is like a little bit elongated. It's a circle is kind of a type of ellipse. So the curve is elliptical. The orbital path of the planets was elliptical, and we know today that it is elliptical rather than the circular oval shape. So this what you can say, the elliptical orbit theory or the law was given by Kepler. So let's now move on to the Kepler's laws, the our topic for today, Kepler laws. So let's see what a conclusion that Kepler drew from the calculations and measurements. He drew the conclusion that orbits of the planets were not circular. As proposed by Copernicus, the orbits were not circular but elliptical, just like as you can see here. The if it is sun here, then planets must be revolving in an elliptical orbit. So first law of orbits, Kepler's first law is called as law of orbits. It's very simple law. Each planet revolves around the sun in an elliptical orbit with sun at one of the foci. So you see, it's very important to understand the concept of ellipse before we understand the law of orbits. So I have made a little bit of points here to make you understand the ellipse. See, ellipse is a curve, as you can see here. It's a closed curve. How it is different from a circle? Let's understand it. So it has a major axis. See, this length here is bigger, so we will call it major axis. This figure ellipse here has two axes, one here and one here, and this axis is the major axis, and half of that is the semi-major axis, which is denoted by A. Semi-major axis. This, in the same way, this is the minor axis, and half of that is the semi-minor axis from here to here. Now forget about the circle, forget about the ellipse. Let's talk about a curve. We don't know the shape of it. Let's see how different curves, which are closed curves, how they are named, and what decides that what will be the name of a particular curve. The concept here is first to understand what is eccentricity of a curve. So eccentricity of a curve, let me tell you, is that is the ratio of the distance of one of the foci. See, I told you already that ellipse has two focus. So one focus is here and one focus is here. So this is not the focus for this figure, but it has two foci. And eccentricity essentially is the ratio of the distance of one of the foci, that is the C in this case, and divided by the semi-major axis. Semi-major axis. So this is the definition of eccentricity. It's a ratio. See how we will make some changes in A or C to really see that what figure will emerge. So let's say C is 0. What do you mean by C is 0? What happens here is that what if you stretch, or you can say you press this figure here inside such that the F here comes at this point. Okay, all the focus is here now. Let's say focus moves here. So what will be the value of C in that case? C will reduce to 0. See, it will reduce to 0. So if the focus is here, the figure now will become a circle, because the C itself has become 0 now. So eccentricity will be 0. That means the figure now, curve now, will be a circle. So circle is a special case of ellipse, where the C value of C is 0. Now let's talk about E becomes 1. That means you decrease this value. So you press it in such a way that your the value of semi-major axis becomes focus. So one thing you need to keep in mind that this is not directly related to Kepler law, but it's a prerequisite for this. You can understand this. It's good for you in mathematics, and you can skip up to this part. So if E is equal to 1, then you will call it a parabola. You will learn about it in your maths classes. So that shape will be called a parabola. Now let's talk about our topic here, the ellipse, in which case E will be less than 1. Whenever it is there, it is the case when it is between 0 and 1, then that shape will be ellipse. As you can see here that A is bigger than C, isn't it? In the case of ellipse, A is bigger than the C. See, in this case we have E less than 1, because this whole figure C is smaller than A. That means the whole value E will be less than 1. Whenever this is the case, you will get a figure called ellipse. Now let's move on to the law of orbits. That's all you need to know about ellipse to understand the first law of Kepler. So each planet revolves around the sun. Each planet is revolving around the sun. Here's the planet, here's the sun. As you can see here, sun is at the one of the foci. Remember, always sun will be at one of the focus. The sun can't be here or here. In the case of Kepler law, this is what Kepler observed. It was at one of the foci, and and planet is revolving in elliptical manner. And here, let's say the AO is equal to OB. These both are the semi-major axis, and which is equal to A. Now eccentricity will be how much? Eccentricity will be SO. Yes, it will be SO. In this case it was C, so it will be SO divided by A, semi-major axis. So you can find the value of SO. SO will be EA. Okay, it will be EA. Now let me erase some part for you so that I'll have the space to really explain to you very important things. In the first law, this the statement that are written in the green highlighted color will be enough for your statement. But there are some very important points called perihelion or aphelion, and what do they really mean? So if E is equal to SO divided by A, yes, divided by semi-major axis. So E was that. So SO was equal to EA. Now, as you can see here that the value AS is the closest distance the planet can be with the sun, isn't it? See, when the planet is revolving around the sun, the closest it can get to the sun is at point A. So AS will be the smallest. Remember that perihelion with P as in Hindi word pass. So you can remember this. The closest is perihelion. So it is the closest approach of the planet with the sun. No. As you can see from here that our perihelion AS will be equal to how much? AS. It will be equal to A total, this A here. Okay, it will be equal to A, take away your SO, minus SO. And what is SO? It will be A minus SO is how much? EA. So you can write perihelion's value, AS perihelion will be equal to A1 minus eccentricity. You need to remember that. You can keep that in mind and note it down. Now let me talk about what can be the biggest distance a planet can have from the sun. This is very important. This point here is obviously is the farthest a planet can be from its star, that is sun in our case, from the earth. So the greatest distance BS of the planet from the sun is called aphelion. Remember that I told you that whenever the word helion comes, it is related to the sun. So here's the sun is what we are talking about. Sun is at the center, one of the focus. So a planet is revolving around the sun. So we will be talking about aphelion or perihelion. So aphelion is the farthest distance. Let's calculate that as well. Now it will be SB. Yes, isn't it? SB, aphelion. So aphelion will be mathematically, as you can see here, that it will be A plus OS. A semi-major axis plus OS. So it will be simply A plus EA. It will be, you take on semi-major axis and it will be 1 plus E. So this will be the value of aphelion. Okay, so and these are the two values of perihelion and aphelion. And one more interesting thing I would like to tell you, that in the case of our Earth, let's say Earth is at the place of the sun. Right now we were talking about any planet revolving around the sun. In the same way, the Earth, if the Earth is at the center and a moon is revolving around it, see our moon, the natural satellite is revolving around it, in that case the closest distance, you will not say it as perihelion, because now we are not dealing with the sun but the Earth. In the case of Earth and moon, a perihelion becomes perigee and aphelion becomes apogee. These are the terms that we need to be careful about. It's very useful that if you're aware about these things. See, so it is perigee for perihelion and aphelion for the apogee. So how can you remember that what is a perihelion or perigee or aphelion or apogee? I have crammed it in a very effective way that has helped me until now. So P for the Hindi word pass. So we can say it is closer. That means pass. So you can remember perigee with that. Okay, you won't get confused if someone asks you. So this was all about Kepler's first law. You need to understand the ellipse, and then we understood what the law of orbits means. So the sun should be at the one of the foci of the that elliptical orbit, and these were the values of perihelion and the aphelion. Now let me tell you about law of law of periods. No, there is another law. Let me see if we have yeah. So the second law of Kepler's planetary motions is called as law of areas. Law of areas. So what is law of areas? Okay, let me draw the elliptical orbit. See, this is the elliptical orbit about which the Earth is revolving around the Sun, and as you can see that, let's, this is the center line, and Sun is at the one of the focus. Sun is here somewhere. Okay, this is a very important law. A little bit tricky to understand, but if you get it one time, you will be good to go. So the line joining, see, uh, let's say the planet is here for the time being. The planet is at the point A. Okay, planet is A at A, and then it will definitely move to point B. Yeah, this is what happens, right? It was at point A, and then it was moving to point B. Okay, so it covers some area. Okay, it has covered some area from A to B, and this area is what we are talking about. So let's say it took 6 months to do that alone. It will be too much. 6 months, it will cover a lot, but let's for the example, for the argument's sake, let's keep it this way. So, and one more thing is that now the planet is at this point. Let me choose a different color for this. This is a winter time, so let's say this, we have green here. So here, let's say this is point C and this is point D. Now let's say from C to D, the same planet took 6 months as well. 6 months as well. 6 months here, 6 months here. See, the time period is same. So what areas of law of area says is that the line joining the sun and planets, the line which is joining the sun and planets, like here, see, the line which is joining sun and the planet sweeps equal area. See, it is sweeping an area. When going from A to B, this line is sweeping an area, which is this area. If you're keeping the time same, if you're keeping 6 months here, from C to D, it will, if it is the 6 months period as well, then it will sweep the, this line will sweep the equal area in that equal period of time. Okay, so let me restate it. Like, the line joining the sun and the planet sweeps out equal areas in equal intervals of time. Okay, equal area in equal interval of time. Which what does it mean in mathematically is that the aerial velocity, let me tell you that aerial velocity, what is aerial velocity? See, first there is a distance covered by the area, like the area is being swept, so in a time, so velocity will be area divided by time. So that is, let's say it is covering area dA in dt time. So aerial velocity will be dA by dt of the planet. Aerial velocity of the planet is always constant, is always constant. So you can simply write it in this way as well, like the aerial velocity of a planet is always constant. It always sweeps, the line joining the sun and the earth planet always sweeps equal area in equal intervals of time. Yeah, so this is what law of areas is all about. You can write it down what I told you just right now, that the line joining sun and the planet sweeps equal area in equal intervals of time, and you can mathematically say that dA by dt, that is the aerial velocity, is constant, is equal to constant. Okay, now out of the syllabus, I will tell you one very interesting fact, that many people up to even master's level, they make a little bit of mistake there. So let me tell you, let me take an situation here. So this is what we can say is the perihelion, right? This point here is the perihelion, isn't it? So apply your logic. What do you think should be the season when the Earth is at this point from the Sun, which is closest? It should be summer, or should it be winter? So if you think it is the summer, it's a simple logic you have applied, that obviously it's a summer, so it's closer to sun, so it will be more hot. But in reality, this is not the case. It is winter when the Earth is very close to the sun. Okay, it is winter in this case. Here we have a winter. So how is that even possible? How is it possible that at this point the aphelion, it must be a summer? But it doesn't seem that way, does it? Because sun is very far away. But let me tell you that the Earth itself is tilted 23 degrees. Okay, it is not a simple circle with the north and south exactly in the axis. This axis actually is tilted. So as you can see here, that let's say in your hemisphere here, the sun will be uh, the sunlight will not be direct on the surface. Okay, it will not be direct on the surface. It will be slanted, because Earth is tilted by 23.5 degrees. Maybe here a little bit different, but 23.5 degrees it is tilted. So in this at this point aphelion, there is summer, because at that point they are aligned in such a way that sunlight is direct on the surface of the Earth. It's direct, so there is summer. And in this case it is not direct, so the heat is not that much absorbed. This was just an extra knowledge. You just need to remember the laws of areas definition only. Okay, let me now take you to the proof of yeah. Before we do that, let's understand what is the law of periods, that is the Kepler's third law of motion. Now, Kepler's third law of motion. I will directly give you what it really. Before we do that, let me get you back to the second law. Okay. Before we do that, let me give you an assignment for this. So let me tell you one very important thing about the laws of areas, is that the Earth itself, the distance from here to here, as you can see, it's not that big as distance from here to here. Yeah, this distance is bigger, but still they are the planet is taking 6 months in both cases, although the distance from A to B is smaller. AB is smaller than CD. Take them the arc length. Okay, this is the arc. So AB is less than CD. How is that even possible that it is taking 6 months for the both distances for the planet? It simply means that from C to D, speed of the planet is high. Yeah, speed is high. Otherwise it won't cover this much big distance in 6 months only. And from A to B, speed is slow. Speed of planet is slow. Now, what does that mean? Why is it happening? Why Earth is doing like this? Why Earth is changing its speed? So the answer for this is that it's trying to conserve the angular momentum. Kepler's second law is the consequence of the law of conservation of angular momentum. Okay, it's the law of conservation of angular momentum. The angular momentum has to remain the same. That is, I1 omega 1 should be equal to I2 omega 2. So see, when the Earth is at the aphelion, sorry, at the perihelion, that means the value of I must be very low. So its omega has to be quick. So the angular velocity will be high because I is low. And in this case, at the aphelion, the the I is very high. Okay, the moment of inertia, that is the mr square, is very high because radius is very high. So omega, angular velocity, has to low down, so it will be slow from A to B as compared to angular velocity from C to D. So in a sense we can say that this is the practical observation for the law of conservation of angular momentum. Okay, this is very important. So you can now try to answer the question in the comment section as well. Why the speed of Earth at perihelion is more than at aphelion. Okay, why is the speed of Earth at perihelion is more than what's the speed at aphelion? Why? Please try to answer this in the comment section. Okay, yeah, now the second law of areas is complete. Now let's quickly move on to the law of periods. Okay, so you can read it out here that the square of the time for a planet to complete one revolution, square of the time, okay, square of the time of a planet to complete one revolution around the sun is taking, let's say, 1 year. Okay, let's say it is taking 1 year. So if you square it, it will be directly proportional to the cube of the semi-major axis of the elliptical orbit. See, this is the what's the semi-major axis? Semi and the major. See, this is the major axis, and the semi-major axis is the point from here to here. This is the semi-major axis A. So let's say in this case it is R. So the square of the time, that is 1 year in our Earth's case, it will be square will be directly proportional to the semi-major axis cube, R cube. This is as simple as that. So this is the law of periods. T square is equal to R cube. Remember, that means that if you take this R here, that means T square over R cube will always be a constant. It will remain constant. T square over R cube will be constant, where R is the semi-major axis. Yeah, understood? If someone asks you the definition of it, you can write it down here, and then you can write the mathematical expression as well. Now, for this law, I will give you the proof as well. Although the proof needs a little bit more understanding of universal law of gravitation, but let's just say I would teach that in the next video, but we can use the formula right now. It's very simple formula, so don't worry about it. Let's understand about how it is even possible, how this result came out to be. Let's assume that the orbit is circular. Okay, let's assume for a moment that the orbit is not elliptical but circular. So it is kind of a circular, almost a circle. Remember that the gravitational force between the sun, which has a mass of m, you can use this figure for this, figure 2 here. So a sun has mass capital M, and a planet has mass small m. So we know that sun's gravitational force is working on the planet. They are the forces are equal and opposite, so gravitational forces are working on each other, but the sun's mass is very high, so this small earth planet here, sorry, is revolving around the sun. That means it's just like a person having a string attached to a stone and then revolving around itself. It's like just like that case. So there is a centripetal force which is working. Okay, there's a centripetal force which is working. The sun is exerting a centripetal force on the planet. So the force here, which is letting the planet to revolve around and just not go like this. Okay, if the centripetal force is gone, the planet will then leave its orbit and go for a tangential path. It will go just out of the orbit, but it's not happening because of the centripetal force. So in a way, that centripetal force is actually equal to the gravitational force of the sun on the earth. Okay, it's actually equal to the gravitational force between them. So I will prove to you, according to law of universal law of gravitation, what's that force is. But right now, let's use the formula for that. So for centripetal force, you need to remember that the formula for that centripetal force is working on the small mass, right? Yes. So it will be, centripetal force will be m with the velocity v. It is moving with the velocity v over r. The radius is r. The distance between planet and the sun is r. So mv square over r is the centripetal force. This is the formula for this. And the gravitational force between sun and the earth is universal constant g, and mass of the sun multiplied by mass of the planet divided by square of the distance between them. So this too will be equal, because the gravitation is provided by centripetal force itself in this case. So mv square over r is equal to gmm over r square. We can write it from this. We can conclude that gm divided by r is equal to v square. Okay, gm divided by r is equal to v square. So and now this is what the relation that we have figured out. Let me take you to another slide here. Let's see that the velocity of the, what is the velocity? What is the definition of velocity? Displacement divided by time, isn't it? Displacement divided by time. But what's the displacement, or you can say what's the magnitude of the displacement in this case? It's simply the circumference, right? It's simply the circumference of the orbit. It will be 2 pi r. So it will be a displacement that is 2 pi r in this case, divided by time taken. What's the time taken? It will be, time period will be, let's say t. So 2 pi r by t. Now substitute the value in the equation 1. This was the equation 1. This was the equation 1. You can put the value of v here. So so the gm over r, this implies gm over r will be equal to 4 pi square r square by t square. We have to square it because it was v square, so we squared it. Now you can remember the time periods formula. So t square will be equal to 4 pi square r cube divided by gm. Okay, divided by gm. Okay, now let's talk about something here. So you have to keep this in mind. So in your I will give you some assignment and numericals. So you have to find, if you have to find out the time period of a planet around the sun, you can apply this formula if you know the value of g, mass of the sun, and the distance between that and the planet. So you can simply find out using this formula. But as you can see here, 4 is a constant, pi is a constant, universal constant g is a constant, and the mass of the sun is a constant for the sun, our sun. So this here, this much value here is actually a constant, isn't it? If it is a constant, that means this implies t square must be directly proportional to r cube, isn't it? They will be directly proportional, because we have changed this constant. This is a constant, and now this equal sign is converted into directly proportional. So in other words, t square divided by r cube is a constant. Okay, this is proved. Hence a third law of periods is proved. This is how you can prove this law of periods. So let me try a numerical based on that. Okay, I'm going to erase it. You can note this down. This is very important, although I recommend you to note everything down in this session. Okay, now let's try a question. Let's say find the number of days in a year. Find the number of days in a year if the distance between the earth and the sun were half its present value. Okay, this is what they're asking about. So as you can see here that they're changing what they have changed. They have changed the distance between earth and the sun. Okay, then they're asking about what will be the change in the time period for the day. Okay, so what you can do is you can pause the video, and try to use the law of periods, that is the third law that we just did. Use that result, that is t square directly proportional to r cube. You can use that result to figure out what can be the answer. So if you have paused the video, tried it, but let's try it together now. We know that t square is directly proportional to r cube. See, the important point here is that we are taking t1 and t2. Okay, so let's say t1 and there is a t2 time period too. So t1 we already know, right? For the present values, let's talk about the present values first. So we know time period for earth to revolve around the sun. It will be 1 year. See, it will be 1 year only, that is 365 days. T1 will be 1 year only, and t2 we don't know. And r, we know the radius as we already know the radius of the distance between sun and earth. One astronomical unit we can use. Let's keep it r1 and r2 for now. Okay, for now. And we know that according to third law of Kepler, t square divided by r cube is a constant. It's a constant always. So that means t1 by t1 square by r t2 square. Okay, t1 square by t2 square will be equal to r1 cube by r2 cube. Because then we have simply what we have done. T1 square is directly proportional to r1 cube, and t2 square was directly proportional to r2 cube, right? And then we have divided these two equations. So remember what I have done here is that I have taken this equation, and then divided it by this equation. Then t1 square by t2 square is equal to r1 cube by r2 cube. Nothing else. You can remember this. This is very useful in numericals. Now, T1 is 1 year, right? T1 is 1 year. And according to the question, the radius R2, if the half is present size, see, it's very important here that we understand the question. So, the radius is half now. So, if R1 was R1 already, the R2 will be half of that R1. It will be half of that R1. Now, you can substitute the values here. If T1 was a 1 and T2 is what we need to find, so T2 will be equal to 1 multiply 1 by 2 3 by 2. Okay, you can elaborate it, try it more here, and then you will find out this. It will be 1 by 2 and 3 halves years. So a number of days in a year, we know that. What are the number of days in a year? 365. So number of days in a year is equal to 365. The new year, that is when the radius is half, so it will be equal to 365 divided by 1 by 2 raised to power 3 by 2. So it will be 365 times 2 raised to power 3 by 2, which will be equal to 365 into 2.828. Okay, so it will be 100, almost approximately 1032 days. So if 1 year will contain this much days. Okay, this was one of the questions that we had tried. Let me give an assignment for the day. Okay, in the next video I will be discussing the universal law of gravitation. Before that, please try the questions that I will be maybe giving in the comment section, or I will be sharing directly. Okay, so give these questions a try. Those questions will be related to the our Kepler laws. So please give them a try and tell me your answers in the comment section. Let me write the questions first. So question 1 is the distance of Neptune, let's say Neptune and Saturn from the sun is a nearly 10 raised to power 13. Okay, this will be 10 raised to power 13. I'm just writing it like this for now. I will make a change here, don't worry. 10 raised to power 13 and 10 raised to power 12 meter respectively. Now assume that they are moving in the circular orbit. Okay, so then what will be the ratio of their period? What will be the ratio of their periods? So this is what you need to figure out. So it was 10 raised to power 13 meter, and this is 10 raised to power 12 meter. This is the distance of Neptune and the Saturn are given respectively. You need to figure out ratio of their periods using the I think Kepler periods law of periods. Yes. So please give your answer in the comment section. Let me recall to you that what are the different topics that we did. We studied about gravitation and different theories that were given historically, geocentric, and then came the heliocentric, and then some improvements in the heliocentric geocentric theory as well. So Kepler gave that, and then 3 laws of Kepler we understood, and we understood the proof of the Kepler third law of periods as well. And now I have given you some questions for the Kepler's law.